Mastering efficient sorting techniques for modern data challenges. In today's era of massive datasets, sorting remains one of the most critical operations in computer science. From database queries to machine learning preprocessing, efficient sorting algorithms are essential for optimizing performance. Understanding the strengths and weaknesses of different sorting methods allows developers to make informed decisions. The choice of sorting technique depends on factors such as dataset size, available memory, and desired execution time. By exploring both classic and modern algorithms, we uncover powerful tools to tackle diverse computational problems effectively. Fundamentals of sorting algorithms. Sorting involves arranging items in a specific order, typically ascending or descending. Common orders include numerical sequences, alphabetical lists, or custom-defined criteria. While seemingly straightforward, achieving optimal performance requires careful consideration of underlying mechanisms. At their core, sorting algorithms compare elements and rearrange them systematically. These comparisons determine the final arrangement, making efficiency a primary concern. Different methodologies exist, ranging from simple pairwise exchanges to sophisticated divide-and-conquer strategies. Time complexity measures how quickly an algorithm scales with increasing input size. A naive approach may work for small datasets but fails catastrophically for larger ones. Recognizing these trade-offs helps engineers select suitable solutions. Bubble sort compares adjacent elements iteratively, swapping them if they're out of order. Despite its simplicity, it has poor scalability with O(n) superscript 2 time complexity. Insertion sort builds the final array incrementally by inserting each element into its correct position. Offers better practical performance than bubble sort for small inputs. Advanced comparison-based method. Selection sort represents another elementary technique where the smallest unsorted element is selected and placed at the beginning. Like bubble sort, it exhibits quadratic time complexity but minimizes swap operations. This algorithm maintains minimal movement of elements, which can be beneficial in systems where write operations are costly. However, its lack of adaptiveness makes it unsuitable for partially ordered data. While not universally applicable, selection sort finds niche applications in embedded systems or situations requiring predictable behavior over raw speed. Merge sort fundamentally transforms sorting through recursion. By dividing the list into halves until single-element subarrays remain, it leverages the principle that merging two sorted arrays is trivial. This divide-and-conquer approach guarantees O(n) log n time complexity in all cases. Its stable nature preserves relative ordering of equal elements, making it ideal for applications demanding consistency. Despite its theoretical advantages, merge sort requires additional memory for temporary storage. This overhead often leads programmers to prefer alternatives when memory constraints exist. Quicksort uses a pivot element to partition the array recursively. On average, it achieves O(n) log n performance but risks O(n) superscript 2 in pathological cases. Heapsort constructs a binary heap data structure and repeatedly extracts the maximum element. Maintains O(n) log n time complexity while operating in place. Non-comparison-based approaches. Certain algorithms bypass direct element comparisons entirely, exploiting properties of the input domain. These specialized techniques offer remarkable efficiency when prerequisites are met. Counting sort capitalizes on integer values within known bounds. It creates frequency counts for each possible number, allowing reconstruction in linear time. This method excels for sparse datasets with limited range but becomes impractical when dealing with arbitrary numeric types or large value domains. Radix sort extends counting sort principles to multi-digit numbers. Starting from least significant digit, it applies counting sort iteratively for each digit place. Its linear time complexity makes radix sort particularly effective for sorting strings or fixed-length numeric representations. Memory consumption increases proportionally with the number of digits processed. Bucket sort distributes elements into buckets according to value ranges. After independent sorting within each bucket, results are concatenated to form the final sorted array. This technique demonstrates exceptional performance for uniformly distributed floating point numbers. Careful bucket sizing determines overall effectiveness. Distribution sort, general term encompassing counting, radix, and bucket sort variants. Requires domain-specific knowledge for optimal utilization. TIMSort, hybrid algorithm combining merge sort and insertion sort. Optimized for real-world data patterns found in Python and Java standard libraries. Evaluating algorithm performance when comparing sorting algorithms, several metrics come into play beyond mere asymptotic analysis. Practical considerations shape implementation choices significantly. Space complexity quantifies auxiliary memory requirements. In-memory operations favor algorithms with lower constants even if big O notation appears similar. Adaptivity refers to an algorithm's ability to detect already sorted portions of the input. Adaptive algorithms avoid unnecessary work when faced with partially ordered data. Stability ensures that equal elements maintain their original relative positions. This property matters critically in applications involving secondary keys or linked structures. Cache efficiency influences actual runtime performance due to modern CPU architectures. Spatial locality benefits algorithms accessing contiguous memory locations frequently. Parallelizability determines suitability for multi-core processors. Some algorithms inherently support concurrent execution through task decomposition. Awareness of these characteristics enables software architects to tailor sorting implementations to specific system constraints and workload patterns. Empirical benchmarking complements theoretical analysis. Real-world testing reveals nuanced behaviors obscured by abstract mathematical models. Modern variations and innovations. Recent research continues refining classical sorting paradigms. Novel approaches combine traditional methods with contemporary computing trends. Block sort builds upon merge sort principles but optimizes disk access patterns. Designed specifically for external sorting tasks involving large files stored on rotational media. This algorithm partitions data into manageable blocks, reducing seek times and improving throughput for sequential read/write operations. Concurrent skip list sort leverages skip lists, a probabilistic data structure, for parallel sorting. Enables high-throughput sorting in distributed environments. By maintaining multiple levels of pointers, skip lists facilitate logarithmic search times while supporting concurrent modifications safely. Quantum-inspired sorting explores potential gains from quantum computation principles. Early-stage research focuses on qubit-based comparison operators. Although currently theoretical, these explorations hint at future possibilities as quantum hardware matures. Practical implementations await breakthroughs in error correction and qubit stability. Machine learning integration presents new frontiers. Researchers investigate training neural networks to predict optimal pivot selections in quicksort-like algorithms. Selecting the right algorithm. No universal solution exists for all sorting challenges. Contextual awareness guides practitioners toward optimal choices matching particular problem domains. For academic study or educational purposes, implementing multiple algorithms provides insight into design philosophies and trade-off analyses. Professionals working with vast datasets benefit from mastering efficient methods like mergesort or TIMSort. These ensure acceptable performance even with millions of records. Development teams handling legacy codebases should understand historical algorithms to troubleshoot issues stemming from outdated implementations. Engineers designing embedded systems require knowledge of lightweight options that minimize resource consumption while meeting timing constraints. Data scientists preparing for machine learning pipelines gain from familiarity with specialized techniques optimized for specific data formats. Ultimately, competence in sorting algorithms enhances problem-solving abilities across diverse technical disciplines. Continuous practice reinforces conceptual understanding. Conclusion: sorting algorithms form a cornerstone of computational theory with wide-ranging implications in software development. Mastery of these fundamentals empowers professionals to build robust, performant solutions. To deepen your expertise, experiment with implementing various algorithms in preferred programming languages. Observe firsthand how different approaches behave under varying conditions.